Okay. Okay, so today's presentation is about cybersecurity data science as a process. This is our typical boilerplate slide here, and people can insert their own picture as needed. Just giving a brief overview of SAS and what it does. So starting off, I'd like to just give a brief overview of the cybersecurity domain and some of the key challenges that are emerging. So we see in the news very clearly the array of threats that are facing people who are defending cybersecurity infrastructure and how quickly they adapt and mutate, and that this is at a global level, and we're seeing emerging and innovative attacks coming out all the time. The challenge for cybersecurity defenders is much more than technical. There's a vast economy behind many of the cyber threats that we see emerging. We've often heard about the deep web and the dark web. So underneath the traditional internet that we interact with on a public level, there's a whole array of information that's accessible through the internet, often through back doors, which is at risk. And this is also a place where people are often looking to gain entry and to compromise systems and to steal information. And then there's also the dark web, which is a range of private and secured interactions and sites where people can interact and also contract with those who might be willing to perform cyber hacking for a service. In fact, this is one of the more worrying phenomenons, which is there's a very vibrant market for anonymously contracting and paying cybersecurity threats and hackers who would be willing to undertake for a fee events and to attack infrastructure and steal information, and that there's an actual price list that's been shown that it's quite inexpensive actually to contract out a service to try to attack some of these sites. As well, there's very sophisticated tools available, and that these are shared quite prolifically. There's also somewhat of a leaky exchange between white hat hacking, gray hat hacking, and black hat hacking, which is that some of the tools and methods that get deployed in white hat hacking, which is consulting to help companies and organizations understand what their vulnerabilities are, some of these tools and methods get quickly shared and made available, or in some cases stolen and used by adversaries who have less than pure intents. So in combination, this has led to quite some challenges for cybersecurity operations centers, so some of which are very sophisticated and large. That stands in the background of modern cybersecurity operations, which is how to overcome these evolving and prolific threats. Now, some of the key drivers that have emerged quite recently that are pushing data science to the front as a way to assist these SOCs is that there's more and more data. So there's big and fast streaming data. The traditional methods that cybersecurity professionals use, which are rules and signatures, are increasingly ineffective, which is that they result in too many alerts. So there's a need for more sophisticated models, in particular those that take into account probability and risk-focused aspects. And that these cybersecurity centers also want to develop integrated awareness of their environments, and in particular to reduce false alerts. And there is a great interest to deploy and utilize machine learning models, although some organizations are reporting some challenges, and some of this deals with confusions, which we will address in this presentation. Behind this all is a lack of resources and a need to automate many of the manual processes involved with investigation and remediation. So this brings us and frames the cybersecurity data science value proposition. So SAS has conducted research that shows quite strongly that the application of analytics in cybersecurity domains is highly efficacious, which is that it does reduce false alerts, and that there's quite a lot of hope in using machine learning and more sophisticated analytics techniques to replace rules and signatures, and that advanced analytics can also assist in real-time detection and decisioning, as a result automating many of the manual processes and reducing labor overhead. And as well, data science can assist in improving data engineering to turn big data or these large volumes of data into smart data. And as well, there's a range of tools that are available to help cybersecurity professionals to visualize much of the complexity that faces them to make better decisions. So I've talked to many organizations, and this picture has evolved, and many of the organizations I visit really would like to achieve this type of process in their SOC organization, which is to streamline the data engineering in their environments, to conduct advanced analytics, and to present very focused alerts and incidents to their investigators so that they can quickly triage and validate those and then remediate them when they've indicated a real event has occurred. So this is the ideal picture, I think, that most SOC employees and managers will nod their heads to. So cybersecurity data science addresses all aspects of that life cycle, that process, and it is indeed a cycle, which is that ideally, if implemented correctly, cybersecurity data science is a process that continually refines and builds a better understanding of the cybersecurity operational environment. And there's two key aspects, which are discovering and detecting. So there are different steps in this process, but they manage the interplay between finding new and emerging types of threats and then putting in place operational methods to detect and remediate. The ultimate goal is to make better decisions and more efficient decisions, in some cases to automate those decisions. And that's really the benefit and hope of advanced analytics, machine learning, and AI. And that's what we can deliver. So to simplify how we're going to discuss this process, I will break it down into three components, which is to talk about the data engineering, the discovery, and then the detection process, and situate advanced analytics as a mechanism of data science in each of those areas. So let's start off with cybersecurity data. So this really is the foundation, as we know, for analytics, which is we have to have high quality data to drive cybersecurity insights. Now, this sounds fine, but as we know, the devil is hiding somewhere in the data. And in the case of cybersecurity, threat agents want to remain hidden in the data. So they're often trying to mute their activities such that they don't show up in routine data analysis. And by those, I mean rules-based and signature-based analysis. So we have to apply more sophisticated methods to look for patterns that want to be hidden. Essentially, finding anomalies is part of the challenge. It's trying to look through an ocean of noise and extract out very targeted anomalies from that highly complex data, noisy data. When we talk about the effort to do that, most organizations who are attempting to utilize advanced analytics in an operational environment report that data challenges are the #1 headache that they experience. And the result is that for most SOCs, they get trapped in a cycle of chasing after phantom patterns. They, in most cases, have large sets of data that they're attempting to analyze, but they haven't essentially validated the methods that they're using. And so they get, again, alert overload. And they end up spending a lot of time chasing after what look like incidents, but in many cases are false alerts. The types of cybersecurity data are quite diverse, and that's part of the challenge. There's a huge number and types of cybersecurity that are surrounding the typical operational environment. And it's appropriate to say that a single granular piece of data can be many, many different things in a cybersecurity environment. If we think about a piece of data as a block, like a Lego, it could be an IP address, a timestamp, a user ID, perhaps a destination port. And when we look more broadly at these, it becomes quite a jumble, quite a pile of data. And not only this, it's coming at intense volumes, in some environments at many billions of events per minute, which leads to this type of data overload, this huge pile of blocks. And so the result for many SOCs is that there's huge amounts of data, many sources, and this leads to many different alerts, many false alerts, and combined with a slow investigation process compromised by lack of resources, many people are struggling in the cybersecurity profession. Now, we do have technologies to help us to store data. So Hadoop and cloud-based storage is prolifically available, but essentially this can often lead to just more and more buckets of large complex data. And we end up with this result of having huge amounts, a lack of context, unvalidated alerts, and multiple systems continually feeding these buckets, ending up with quite a jumble. Now, one approach and a very good guidance to people attempting to improve this process is to try to package up the data and to sort it into self-similar components so that we can analyze it, and then package it up and make it available to applications and also people so they can remediate and identify incidents more easily. This is really where we get into data engineering, which is taking unstructured and diverse and distributed data and funneling it through pipes and processes so that it gets sorted and analyzed efficiently and presented then to the right applications and to the right people. And in particular, when we're talking about data science, getting it to efficacious analytical models that can find anomalies and incidents. So one thing that is very important is that we need some type of structure for the data. And this is where we can advocate the use of frameworks and ontologies in the cybersecurity realm, which is there's a number of different ways of framing cybersecurity incidents and threats and discussing how threats undertake an incursion. And from there, we can also apply data ontologies, which are ways of structuring and sorting data so that it can assist in the data engineering process. So one best practice is to adapt and adopt frameworks and ontologies for cybersecurity in order to sort and move data forward in the operational chain. So this essentially leads to the result that we have data in nice compartmentalized areas where we can then sort it and make it available to cybersecurity professionals and to applications, turning essentially these giant piles of data into cleaned, integrated, ready to analyze data. For this, SAS itself has a range of best practices for managing big data. There's quite a nice white paper we have giving an overview of best practices surrounding big data management. And of course, there's a number of technical solutions that we offer to assist with the big data engineering. The ideal result then is we get somewhat of a workshop where there's a range of sorted and organized cybersecurity data that is made available for operationalization. So this brings us then to the topic of discovery in the cybersecurity data science field. And again, if we think about cybersecurity data science as a life cycle, we're thinking here about framing, exploring, and engineering data so that it's made available to models. And this is a very crucial process. And perhaps some organizations don't invest enough in this, but discovery overlaps essentially between data engineering and detection. A lot of organizations seem to want to go right towards detection, but if you don't do your data engineering and data discovery beforehand, you're guaranteed to get into the trap of raising phantom patterns and false alerts. So cybersecurity events by nature, because of the volume and the diversity, are essentially quite complex, and they're also irregular. So we see quite chaotic events that are difficult to predict. We see data coming in spurts, and it's difficult to predict exactly what's happening. So one way to start to reduce that complexity is to start framing some of the key entities that exist in the cybersecurity domain. So one good question to ask at the very beginning is, what is a user in any particular environment? And that can sometimes be a bit more complicated than just saying, well, a person, because what we do find is that many organizations share user IDs, or they may have machines with user IDs, and there may be different types of data that are associated with a user, and that those may need to be combined. So, and an example that has for an environment where they're lending out temporary IP addresses, such as using DHCP, it's not necessarily the case that an IP address can be easily associated with a single user ID. So there needs to be a primary understanding of how one would like to represent a user to systems in a operational environment. And for this, one thing we might like to do is to, for instance, build up a behavioral profile, which is to frame the types of data that represent a user and would allow us to analyze their behavior. And one good way to get started is to, after the data has been engineered appropriately, to present it visually to experts who can help to interpret it and provide feedback according to what they're seeing in the operational environment, and provide feedback on how they would frame users and user dynamics. So for this, we can offer self-service visual analytics. So this is sort of a dashboard on steroids, which is we have the ability to provide advanced analytical features to cybersecurity professionals, so they can do their own deep and advanced data analytics in an integrated environment. So from here, we will want to also try some advanced methods to analyze the data and to derive out perhaps new measures. So one very powerful technique that can be used in the cybersecurity area is network graph analytics. So it fits very well with cybersecurity because we are talking essentially about networks and network behavior and devices and people interacting in networks. So there's a field of analytics that specializes in deriving out patterns from network graphs. And this is not only for visualization, but also for deriving out statistical measures, such as the measure of centrality or reach across a network for different devices and users. And this helps us to categorize and qualify the behavior of different entities inside of cybersecurity operational environments. Another thing we can do is to conduct feature selection and then to extract out new measures. So one thing we can do is to look at the frequency of usage and levels of usage, to look at byte traffic and look at how many hours a particular device or user is online, for instance, per day or week. And one of the things that we do see looking across many different organizational networks is that there's often what's called a Pareto principle, which is otherwise known as the 80-20 rule. And this is observable in many natural phenomenon, but also in network behavior, which is we can often see that there's a large group of 80% of users who are not on the network that frequently and are just doing basic activities, and another 20% who are very heavy users. These are very sophisticated computer users who are doing a greater range of activities, have larger byte traffic, and are on the computer many hours a day. So the ability to identify those users and devices and potentially segment them, for instance, into a peer group is very valuable in sorting through some of the complexity of these operational environments, because you can label these users and attempt to track them separately. Someone who is a sophisticated user who spends 80 hours a week on their systems, we'd want to treat them differently than someone who's on 5 or 10 hours a week. And so this is a good example of where we would want to extract out a feature, perhaps to put forward a measure of technical sophistication and then label that so that we can disassociate those users and devices that are relatively inactive from those that are highly active. We can also apply other techniques such as to reduce the amount of data, to reduce the amount of variables that we're dealing with. So an example here would be dimensionality reduction. So we can use a technique called principal component analysis. So this lets us look across a large range of variables and to identify patterns and similarities amongst similar variables such that we might be able to aggregate them. And so this can lead to a reduction in the volumes of data and to greater efficiency, therefore. So if we see a high statistical correlation between particular measures, we can aggregate those into a bucket and name them, and then therefore reduce the data set and improve our ability to push these signals forward in the operational environment. Another method we can use, and this starts to get into the topic of machine learning, is unsupervised machine learning. So unsupervised machine learning is a technique that allows us to ask questions when we don't know exactly what we're looking for. We may have a large set of data and we want to see similarities. So an example here would be we have a group of users with some details about their usage, as I mentioned earlier, hours per week, amounts of bytes conducted, their number of IPs they connect to, and we'd like to ask about which groups these users statistically fall into. Well, this is where unsupervised analytics can help. So using a method such as cluster analysis, the machine will identify statistically self-similar groupings, which can be then put forward as peer groups. So in this example here, which is real network data that we analyzed, we were able to find that there were 20 self-similar groups. And so the recommendation to a cybersecurity operations center would be to consider perhaps bucketing their users into these groups because they behave in distinct ways that are statistically similar. And we have found actually, and looking at a number of networks, that these patterns hold over time. So I've done some work where I've been looking at data over the course of a year, and there's a high degree of consistency that users tend to stay in their behavioral groups. And so that's quite interesting because it proposes a statistically valid method to bucket and put users or devices into peer groups. So at this point now, we've started getting into what can be called a toolkit. So we've shown you several different methods, and essentially data science is a whole toolkit of different methods, of advanced analytic methods and statistical techniques and machine learning methods that can be connected together to realize certain goals. So when we're talking about discovery, we're talking about looking for unknown patterns to try to qualify complex patterns. And this is the first step to getting a handle on complex behaviors in a cybersecurity environment. So that's the first step towards really applying data science methods. And this brings us to the third step, having looked at data and having looked at exploration or discovery. We now look at the topic of detection. And one thing I mentioned is that many organizations have tried to do this first, and they floundered because they haven't done the preliminary work to understand their data and discover patterns. But once that's done, we can really do detection effectively, which is that if the groundwork has been laid and we set up a foundation, then detection models can be put into place. So this is the point where we actually want to build detection models, validate those, and deploy them into operations. So returning to the analytics toolkit supporting cybersecurity data science, we're now talking about putting in place detection models that have been enriched with engineered data, with patterns that we've identified during the exploration process. And this will allow us to be able to, in some cases, detect incidents. And it's appropriate to say now, at this point, that analytics can be considered a continuum, that if we put the foundational work into data quality and data discovery and conducting diagnostics and doing statistical analysis, it's at that point we can really realize the benefits of more advanced analytics, which is prediction, and further on from there, optimizing and prescriptive analytics, and even doing semantic analytics. So when we talk about predictive analytics, what we're talking about is supervised machine learning. And so at a very high level, this utilizes labeled data or known incidents where we have a very clear example of what we consider to be bad. And it could be based on professional opinion or expert input, or it could be an actual recording of a known incident that's been recorded in data. And that this data is put forward as an example of what we consider to be bad. And it's used to train sophisticated predictive or supervised machine learning models. So we feed that data through an algorithm, which then trains itself to recognize the subtle indicators of attack that are resident in that data. We combine it also with normal data. So the model also understands what is considered non-threatening or normal. And from there, when we feed new incidents in, the model will identify what it considers to resemble something threatening and to disassociate that from the normal or expected events. So just to summarize, supervised learning relies on labeled data. And from that, it allows us to classify and predict. There's a whole range of different types of models, and some of them you may have heard of, such as decision trees, random forests, and naive Bayes methods. And increasingly, we're also seeing a lot of innovation in deep learning predictive models, which is a type of a nested neural network, and that these also can be highly efficacious, and this is also something that is supportable. Some of the caveats with predictive machine learning, as I mentioned, is that it does require labeled examples to train the models. And importantly, we can't rely on suspicion alone. We can't put forward perceived anomalies to train the models. All we'll get is more perceived anomalies. So it's important that we understand that there needs to be labeled incidents and labeled examples to train the model. As is similar in the fraud realm, also in the cyber realm, it's often the case that these incidents are very small in relation to normal data, normal incidents. And so the data is often skewed in these models. And so that can present some challenges in training models, but that's something that can be accommodated. So at this point then, having covered both unsupervised machine learning and supervised machine learning and talked about data engineering, I sort of like to propose that what essentially machine learning is, and a way to think about it is as a very complex vehicle for data. So it's made of data, which is that all the types of data that have been gathered and engineered feed these models, and they actually do things then, which is make decisions and create efficiencies in operational environments. And that's very much the case. So if we've put in the effort to engineer our data, discover patterns, and then to properly train models, they can do some very sophisticated things for us. So behind this all, we've now talked about finding unknown patterns using unsupervised methods in exploration and discovery, and supervised methods, which is finding patterns based on known types. There's an interplay between the two. So there's a reason why I've distinguished discovery from detection, which is that the two ideally can feed off one another, which is that if you conduct unsupervised analytics to develop patterns, such as different types of users, you can then put those forward as features in supervised machine learning, which will make the predictive machine learning much more effective. So this is part of the life cycle, which is continually understanding the hidden patterns in your data sets, particularly as new threats evolve, and using those to make sure that your supervised methods are up to date and are efficacious. This gets into another best practice that SAS has written quite a lot about, which is the analytics lifecycle. So in a sense, again, there is a continual life cycle between development of detection models and the discovery and exploration of data, and that this should continue to cycle to ensure that models are up to date and are working properly. In an operational environment for cybersecurity, getting into how we stage these, there is a recommendation that you don't necessarily need to do away with rules-based and signature-based methods for detecting cybersecurity events. In fact, those can be part of your solution. They can contribute to some of the alerts that you detect, but that you should add on to this the unsupervised methods, and ultimately then push these forward and analyze them and detect real events and disassociate them from false positives, and use that to train supervised models. And if you continually cycle the data in this respect, you'll get machine learning models that are self-improving. So it's not completely machine driven in that there's a human in the loop in this model, which is that we're assuming that investigators are part of this and that cybersecurity experts are helping to develop features and to improve the data engineering behind the scenes to make sure that the right data is cycling through the process continually. When we talk about then architectures in these operational environments, part of the recommendation and a best practice would be to segment out your exploratory data analysis from your operationally focused detection. So a lot of organizations in the past 2 to 3 years have developed cybersecurity data lakes, and many of them have simply dumped a huge amount of log files and cybersecurity data sources into large repositories. But the argument would be that that is more appropriate for exploration and discovery, and that what you would ideally want to do is have a separate, more refined environment where you're conducting operational detection, where you maintain your models and develop the models and maintain them and validate them, and that there's interplay between these two operational silos, that they're connected to one another, but that there's a formal separation. And one should have the detection silo should have a much smaller data imprint. It should be much more focused and not attempt to store all the data all the time. This somewhat goes against the industry advocacy because a lot of vendors, remember, their business model has to do with data storage and processing overhead. So they may not be necessarily motivated to assist in reducing data sets, but we feel that this is essential for cybersecurity detection effectiveness. So now I'll move on to a few short examples of what we've done to realize some of these best practices and some of these methods. which is we've indeed put this to use in several hands-on cases. So one of them is our flagship product, SAS Cybersecurity. So behind the scenes, SAS Cybersecurity does a lot of the hard work of stitching together complex cybersecurity data sets and events into a unified view. So this is a non-trivial problem, which is the data comes in at such a speed and volume that it's difficult to stitch it together. But that's essentially what our solution does. It creates a unified view of diverse cybersecurity events and data sources, and then pushes those forward towards analytical models. Now, I'll move on to another example. This is a more focused example for a German client where we developed an approach towards detecting DDoS attacks, which is denial of service attacks. And this particular client had a concern about botnet based malware, which were being used to attack infrastructure. So for some background here, there's a type of botnet called Mirai, which is a malware infection that infects Internet of Things devices. So conference phones, cameras, smart TVs, routers for internet service. And it had attacked and infected a very large number of devices. And no one had known this until they decided to launch an attack. So once this large botnet was assembled, the attackers were able to bring it to bear to deny service and attack organizations and attack their infrastructure. Now, the issue that has been somewhat vexing is that attackers have continued to evolve the core source code, which has been made available in the dark web, and they've continued to evolve and make this a more and more sophisticated approach. So there's at least 13 variants have been reported, and now more that are running around and used to infect various devices. So what we did is we first developed a deeper understanding of the infection life cycle of how this particular exploit works. And so in the case of Mirai and its variants, it was infecting Internet of Things devices. So the first stage of infection was looking around on the public internet for particular devices that had vulnerabilities and perhaps hadn't had the default password reset, for instance. So people who had installed a router or a smart camera and not changed the default password, which were easily attackable then. And then these were infected. So after a large number of these devices were affected, then the attackers moved into a surveillance phase where they looked for, they started looking for targets to attack with their botnet. So they started surveilling different corporate networks and organizational networks to see which ones might be vulnerable to this attack. So they used the IoT botnet army to start looking at corporate vulnerabilities. And so we saw this data in a network of honeypots. Honeypots are devices that are set up to look like corporate servers, and information was collected from these at a large scale, and we analyzed it to see the effect of these scanning events and the surveillance events. So this in a case that happened last year, led up to a mass attack that had affected several organizations. However, in analyzing the data between the infection, the surveillance, and the attack, we were able to see some early indicators leading up to the attack. So this was very promising because just by visualizing the data, we saw some clear signs that up to 2 weeks before the attack on one of these organizations, we saw some surveillance going on and some key measures that were peaking outside their normal bounds on the honeypot network that were indicating something was going on and that there was a preparation for a mass attack. So this was the first step, and it's aligns very well to the data engineering and the data discovery parts of the cybersecurity lifecycle, which is we engineered the data and we discovered in the data certain key features. And the next step to this would be to push it forwards to a detection model, which is to extrapolate the key variables and use them to detect and to put in place a detection model for early warning of these types of attacks. So the last example I'll use, it gets back to the user behavioral analytics, which is the application of unsupervised machine learning to extract out peer groups. So for a client in Europe, what we did is we took a range of cybersecurity data that was collected over several months, and we analyzed it in order to find key peer groups in that data. And indeed, that's what we saw, which is conducting cluster analysis. We saw some characteristic behaviors that allowed us to segment out different types of users. As well, and interestingly, the unsupervised technique also rejected some of the users, which meant that they were doing very highly unusual things that didn't match any of their peers. So there were about 11,000 users on this network, and we found a number of the users were so unusual that they couldn't be classified in any type of group. Now, it was interesting to find that most of these were unlabeled machines, that they were essentially machines with a human user ID, but they just weren't labeled. And that this is quite frequent. What we see in operational environments is that the labeling and the peer groups, often coming from CMDB or configuration management data, is not of a high quality, and that there's often some mislabeled entities, devices, and users in those data sets, and that it's very important to help and to improve detection if they can be relabeled and taken out of the human user group and put into a machine user group, for instance. So basically, using unsupervised machine learning, it allows us to, not knowing anything about the environment, develop an idea of the patterns that are resident in the behaviors of the users and devices, and to put these forward and suggest improvements to the labeling of these entities, which therefore focuses cybersecurity protection and detection. So basically, once these peer groups are put forward, we can label them because they have characteristic behaviors, and they can be tracked potentially separately. And from there, once a user or device deviates from its statistical peer group, that can be considered a very focused anomaly, as opposed to trying to look for anomalies amongst the whole set of users. So for instance, 10 or 20,000 users, in which case you're dealing with a great deal of noise and chaos, and you're not being very focused about looking for anomalies. So again, this method allowed us not only to find peer group patterns, but also to find anomalies or highly unusual entities that we immediately put forward. Okay, so that brings us towards the end of this presentation. So we've given an overview of cybersecurity data science as a process that unites data engineering, a process of discovery, and detection. And we framed this as a process, a cycle, that if done correctly should be cyclical and self-improving, that ideally the insights gained from detection should feed back into better and improved ways of framing the data, developing new features, which improves discovery and then leads to more refined models. And ultimately, the goal is to make better and better decisions, and ultimately to automate some of the decisions that need to be made such that they're more efficacious and targeted. And the important thing to mention here is that we're not an advocate of complete automation. We think that any vendors who are advertising that, advertising a magic box that's going to do things automatically, are missing the point, which is much of this depends upon domain experience and expertise. And the threats and the attacks that are happening on the other end of the chain are people. And people are quite unpredictable, and they're also savvy. They know that they're being watched, and they look for ways around being detected, and they're continually evolving. And as a result, we will always need people to second guess and to continue to analyze data in order to refine models, because that's exactly what the attackers are doing. So I mentioned earlier that many organizations get trapped in this cycle of chasing phantom patterns. Our advocacy is that if you do the data engineering and the discovery, you can then do detection. And not only that, once you're doing effective detection, you can optimize resources and investigations and start working towards a risk optimal solution for managing cybersecurity security operations. So that brings us to the conclusion of this presentation, and this is an area where we can put white papers. We have many, and do additional advocacy. And I also have some of the articles that SAS has sponsored and some of the references that we can point to that will substantiate our expertise and thought leadership. So thank you for your attention. With that, I guess I'll leave the recording on, and if anyone has any questions that you think pertain to this or suggestions, please jump in.
Scott, this is John. That was incredible. I think finally it's such a relief to see how like your flow of everything in the slides and then the content of your talk makes this super understandable by anybody out there that's both expert as well as layperson. So it's refreshing to see kind of that end-to-end roadmap that you've put together, and I'm excited. I'm very excited about it.
Oh, well, great. Thanks, John. Well, I'll be certainly available to help as you build the deck for the event. A lot of the best practices came originally out of our fraud practice, so you'll probably see a lot of similarities. I actually started at SAS in the fraud practice, so I think that there's a lot of opportunities to leverage what we're doing in fraud and cyber, and part of the challenge is that a lot of cybersecurity professionals believe that their domain is unique and special, which is not always the case, especially when we're talking about data analytics. And so there's two main things that people get upset about, I think, having invested their career in cybersecurity, that people may be resistant to new methods, which is machine learning. So we need to humanize it and explain and simplify it. And there's the other thing of a fear of being automated. A lot of management is responding in the market to these magic boxes, and we need to allay fears that these solutions are going to automate away people's jobs. That's not at all the case. What we want to do is encourage that these are new tools to make their jobs more effective, and that people, cybersecurity experts, are in the driver's seat. Yeah, yeah.
Scott, I think these are a really good slide, and I'll be attending the conference in May.
Mm-hmm.
And do you know? I guess, do you or John know like who are the target audience typically that attend these conferences?
We heard it's quite a mix. This IACD conference is an open forum, and it's positioned as an exchange venue to create synergies between the private market and the public services, so that security intelligence people working in the government can learn from some of the best practices in private industry, which is often moving faster than they are. And I expect that, as what I understand, is that some pretty high-level people from Homeland Security and NSA will show up to learn from industry best practices at this meeting, as well, from both a management perspective and perhaps also engineers and technical experts. The problem, I guess, and the challenge is that when you talk about cybersecurity data science, you're conflating several expert domains together. So there may be people who show up who are very skilled cybersecurity professionals who will
Mm-hmm.
want to gloss over the background on cybersecurity, and then you may get data scientists who already understand the basics of data science. But what's unique here is there's a real lack of cybersecurity data scientists. So we kind of try to shoot for the middle of the room.
Mm-hmm.
Yeah.
Mm-hmm. Right, right. Oh, right. Yeah, I mean, these are really good presentation. Good job.
Oh, thank you. Well, happy if people want to add to this, and we could. I'll post the deck and send it, and it would be great to keep it alive and continue to add to it.
Mm-hmm.
Hmm.
I think this is a great high, representation of what's involved and giving a good uh, uh, direction and all the steps that's involved. I think it's easy to see different at different stages what's involved to get to that the destination, which is a, like you stated it, which is a cycle still. But from the raw data to the point of getting detecting the intrusions, yeah, there are various stages and um, events that must occur. So I think this captures that complexity as well as the what must take place very well. I think this is a great presentation. Do you know if there would be like opportunities at these type of um, conferences? I guess that would be something that those who have attended can tell, like if they can, um, if there will be opportunities to share some of the like how to type of um, you know for instance having a engaged in some of the POCs. A lot of our customers are sitting on like you said various data lakes. They are collecting multitude of data sets, and yet they don't know how to use it. For instance, one of our government clients, they have SaaS tools they already purchased, and they don't know how to use it effectively. So, when we show them, even with one set of data that they have that's coming out of one tool, security tool, we can easily apply what's already in their arsenal, how to basically feed that data into, for instance, VIA, and basically utilize VA reporting dashboard, and basically to show how to gain better insight into that data set. For instance, who is generating the most alerts, and what type of what type of sources they are, and then doing simple enrichment and what have you using SAS. Their interest level just shoots up. They can basically see the it's almost a little taste of what analytics is going to do, because so I'm just wondering if there would be some type of opportunity for us to even do that type and share that as a how-to kind of thing, and yet show the value of basically we would be doing that using SaaS tools, and perhaps share that, and then give them even more real life, something that's obviously we will have to sanitize a lot of this data and what have you, but perhaps bring that into this type of conferences and walk them through, so that they can see sort of like they can almost touch it, what the analytics is about. Obviously this is not, it's only covering perhaps part of it, but they can see the transformation of this raw data into something that's almost actionable.
Well, I'd mentioned that Alex had shared a great deck from some colleagues in South Canada on fraud analytics, who had some deeper examples, and they have written some code, some sophisticated analytics models for fraud use cases, and I'll be talking with these people to see if we can re-leverage some of the code and examples for the cybersecurity realm. And so that I think this deck here is more for an L2 type of presentation to pique people's interest, and a good outcome would be to be invited to particular organizations to give an L3, which is then to show some of the examples working. So that's probably some of the advocacy, is that at the end of the presentation say, well, we've only had short time here, but if you like, we can come and demonstrate some of these methods working. And that's when we can go into the hands-on examples, and I'd be very happy to continue working on making those demos and building those examples.
Yeah, this is Liz, and a suggestion is if there is also a way that we can talk about maybe some of the concepts in a generic way. Maybe we could work on something that would be like a LinkedIn post. I mean, that would be something short. Hey, we work with organizations, and here's some best practices on how some of the best organizations do it. That might be an alternative way to get our point across. But obviously, I know customers usually want to know, more specifics on how others are doing it too.
Mm-hmm. Yeah, definitely. I think we've seen in our industry that they can be very shy about sharing. A lot of organizations seem to be somewhat reticent about sharing any details about what they're doing with cyber, but yeah, we should always try to see if we can find people who'd like to promote best practices. Yeah. I'm meanwhile working on some academic research on this topic and have gotten some best practices based on interviewing cybersecurity data scientists. And so I'm compiling that right now, and we'll have a focused article on that available this summer.
Excellent.
Yeah. Well, great. I don't want to take up people's lunch. I know the blood sugar could be getting low here, so I'll post the deck. And well, thank you for your time, and I'll stop the recording. And John, I'll be very happy to follow up with John once he and Patrick are ready to go forward.